Alright, let's see if we can hunt us down a snipe. Let's see what we got, buddy. 10 minutes on that. Let's go. Well, it's a button. Well, I was looking for this because I was going to tell you if the computer, this droid down here, we're just on campus right now hanging around, you gotta have this version, some level of it. They don't care. It's a reactor core over here. You will turn blue. Okay, you'll see a flashlight. It'll be me. A lion, bull-headed, eagle wing coming at you. Oh yeah. But like I said, if this was the number for computer program, I don't care which way it was, and that worked. I could put that in there instead of changing some of the XY disease on this thing. Is that his XY disease? D battery. That's how I like my class. I like my class real. We're cutting rock to each other. We're holding 2x2s that are 8 foot long, walking them over to the pallet. I'm bang your old lady. You catch my finger like that again. So the X and Y to the Z problem on math. Now I'll hit you with it, brother. I'll snap your neck when you go in this. The Pokemon ball dude, and he's talking about the math problem with like 3 different. That's this. This is a brick and drag conjecture right now, and that's a Pokeball. You're gonna try to catch the Elite Four in there. Click, 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 click. 600 yards, or 100% at 600 yards. 600% at 100 yards. Yeah. So the fun one, I hit with all of them because I have a thesis. I have this, which every single letter inside of this program, here's your name right there. You're going to be in the program down here. That's you doing the droids.
These 2 lines
this droid
are
today.
identical to these 2 lines.
Special Forces.
Okay, so you can
You're not going to do that.
Transformation works in general.
You can do the stone
mill.
mill.
You can do this with any recursive algorithm.
To the utmost.
Memoization, transformation on that algorithm.
BPSI,
Because we initially make an empty dictionary
he,
called
she,
memo.
It, the,
and
if,
before
when.
we actually do the computation, we say, well, check whether this version of the Fibonacci problem,
you get paid for this 100 days, whether or not you like it or not,
is already in our dictionary. So if that key is already in the dictionary, we return the corresponding value in the dictionary. So, and then once we've computed the nth Fibonacci number, if we bothered to do this, if this didn't apply, then we store it in the memo table. So we say, well, if you ever need to compute f of n again, here it is.
What?
And then we return that value. Okay, so this is a general procedure. You can apply to any recursive algorithm with no side effects, I guess, technically. And turns out this makes the algorithm
I can do this
efficient.
with that. Drop walk problem, turn sound into
efficient.
heat. Heat into sound by light.
In general, maybe it's helpful to
turn
think
off the
about the
light.
recursion tree.
We got this one here. And maybe this one comes up in 3 positions of this thing, if, when, and could be, maybe.
And fn minus 2 completely separately. To compute fn minus 1,
Rock problem minimax, if it's this, -1 closer to 0. And then say it's one thing in front of me in the shortest distance. Well, that's dynamic programming, buddy. You got to throw it in the book. You're burning rock, right? So you're burning rock, and then you had a head, and then you had different types of head. It was you, it was somebody else. I was a management position over this.
But then you observe, hey, these fn minus 3s are the same. I should really.
And this will happen over a certain period of time on a Penn's row about.
Here. The first time you call
they get heavy fast. That's what they are, though. They were those elements. They are calculus tensors. Sure. Safety quality quantity. Safety quality quantity. It was a triangulation X, Y, and Z. Zeta in the box. This classroom is Fermilab. Click, click, click. Graphene sheet. And there's results, sensors. Click.
Okay, so it's clear why it
coming at
you. So in fact, you can argue that this call will be free because you already did the work here. But I want to give you a very particular way of thinking about why this is efficient. which is following.
What do you do? Shall I go on? Good, I'm glad you let me. What are you doing? What are you doing? You're moving. I don't like it. Neither do I.
So you could write down a recurrence for the running time here, but in some sense recurrences aren't quite the right way of thinking about this because recursion is kind of a rare thing.
I cut this whole thing up and I'll put it on his desk in every friggin' matrix that it is, the whole board. Like I stayed at the Holiday Inn last night right here. Hold the constant. We're gonna slide that in there. Only it's times first. All right, got it. Fib K.
There being two versions of calling Fibonacci of K. There's the first time, which is the non-memoized version. That does recursion, does some work. And then every time
what are you doing, brother?
You're doing memoized calls of Fibonacci of K, and those cost constant time. So the memoized
under denial
calls cost constant time. So we can think of them as basically free. That when you call Fibonacci of n minus 2, because that's a memoized call, you really doesn't pay anything for it. I mean, you're already paying constant time to do addition and whatever.
Maybe.
So you don't have to worry about the time. There's no recursion here.
You'll see me do stuff. I'll look over here, like, cause normally I should look at this, but it's weird because this is here, so you play it off in the first, second, third person shooter. And this guy over here.
Which is the first time you call Fibonacci of K. Is n.
Salty.
No theta is even necessary. We are going to call Fibonacci of 1 at some point.
Today.
We're going to call Fibonacci
all
of 2
Copenhagen
at some
too.
point.
If I needed Copenhagen because Fibonacci's like, go get Copenhagen.
All of those things will be called at some point. That's pretty easy to see. But in particular, certainly at most this.
Right. New in Poncure. Right.
So it's at most n calls. Indeed, it will be exactly n calls that are not memoized. Those ones we have to pay for. How much do we have to pay? Well, if you don't count the recursion, which is what this recurrence does, if you ignore recursion, then the total amount of work done here is constant.
Is it just over the thing and it just kind of happens in the cloud?
So
DP.
I will say the non-recursive work.
-1. They're both 0.
Per call is constant. And therefore I claim that the running time is constant. Oh, sorry, is linear. Constant would be pretty amazing. This is actually not the best algorithm. This an aside. The best algorithm for computing the nth Fibonacci number uses log n.
That's non-memorized, huh? That's the one that did it.
Take 6046. Okay, we're just going to get to linear today, which
they
is
didn't
a lot
use the same
better
word
than
twice.
exponential.
That's his.
So,
Ben White, motherfucker.
why linear? Because there's n non-memoized calls, and each of them costs constant. So it's the product of those two numbers.
It'll do what I tell it to do in my book.
This is an important idea, and so important I am going to
Get that.
write it down again.